my great pleasure to introduce Cynthia Sturton. Cynthia Sturton is our security candidate in Excel for both CSE and EE, so it's great to see a collection of both CSE and EE people here. Cynthia is first and foremost a security person, but with a large number of kind of cross-disciplinary collaborative interests, and we'll be talking about one aspect of her work, focusing on model checking. Cynthia has done a large number of other things. I first remember seeing some of her work on electronic voting, how do we make better electronic voting machines, and also how can we make better malware as a type of important things that we need to be doing. And if you're familiar with the computer security community, you probably are familiar with the top 3 conferences, Usenix Security, Oakland, which is not in Oakland, but called Oakland, and CCS, and Cynthia was most recently on the PC for Usenix Security. There is this thing called cloud computing. I think we're all familiar with it. It uses something called virtualization. And so one of the things that is very important is how do we actually do this securely? And so with that, I'll turn this over to Cynthia to talk about secure virtualization.
Thank you. So as Yoshi mentioned, my research is in security. And in particular, what I like to do is I like to look at the lowest level of a system, so hardware or system-level software, and try to establish a solid foundation of trust by proving security properties about that aspect of the system. And I do that by looking for ways to make formal methods, formal verification methods, practical for this level of the system. So my thesis focuses on verifying security properties of virtualization software, and that'll be the first part of my talk. Then I've also done work on applying verification methods to prove security properties of hardware, and I'll talk a little bit about some of the projects I've done there. And then finally, I'll talk about some future projects that I'm really excited about. So let me start with a little bit of background about virtualization software. One great example of such software can be found in cloud computing, specifically what's called infrastructure as a service, or IaaS-style cloud computing. And with IaaS, a user has the illusion that she can boot up her own personal machine in the cloud. So when she wants a machine, she sends a request for a new machine. It starts up in the cloud. And when she has this appearance of having her own personal machine. When she's done, she sends a request to the cloud provider to stop her machine. And she only pays for the compute time that she used. So in reality, the cloud provider maintains very many servers. And when the user requests a new machine, she's really getting a new virtual machine on one of these servers. And while she has the illusion that she has her own virtual machine or her own physical machine, in reality, there can be many virtual machines sharing the same physical hardware. And virtualization software is the layer that allows multiple operating systems to share a single hardware platform. So here's a small sampling of some of the businesses and institutions that are using this IaaS-style cloud computing. It's a large $5.6 billion industry. It's expected to grow fourfold in the next 5 years. And there are all sorts of users in this space. So we have online shopping sites, social networking sites, universities, news media organizations, and the US government and healthcare industries are starting to get into this field as well, or this area as well. But they do have some concerns about security. And if we go back to this picture, we can see why that might be the case. With multiple clients sharing a machine, it's possible to end up with some natural enemies sharing the same physical hardware. So this is a made-up example. I have no evidence that this has actually happened. But you can see where we might get into trouble here. And in addition, we also know that spammers and command and control channels for botnets are also using these services. And these are guys who are, or users who are paying customers. So it's not like they've hacked into the cloud provider system. They're paying customers, and they're using these services. So you can see that it's possible to have unfriendly or even adversarial co-tenants sharing the same physical machine. And when one co-tenant has an incentive to read or write the memory belonging to another tenant on that machine, we get into a dangerous situation. So we need to make sure that that just isn't possible. No matter how hard the co-tenant, the malicious guy, tries, it's just not possible. So to give a high-level view of how this works, in order to allow multiple operating systems to share a single hardware platform, there's a layer of virtualization software that virtualizes the hardware underneath. The virtualization software, in addition to virtualizing the hardware, it also provides isolation properties so that one guest can't access the memory belonging to a second guest. So the hypervisor is providing these really great services. It's virtualizing the hardware. It allows multiple operating systems to share a single platform. It's providing these isolation guarantees. These are all really security critical properties. And what I would like to do, and what I focus on in my thesis research is can we have some way of showing that it's actually doing this correctly? It says it's providing all these great security properties for us, but can we verify that it actually is doing that? So here are some of the reasons that maybe we should be worried about the correctness or the trustworthiness of virtualization software. First, it's large. The software that does this is a large piece of code. So this 150,000 lines of code, this number comes from the Xen hypervisor. Not only is it large, but it's complex. So the management of virtual memory is a complex software that manages the guest view of memory down to the physical, actual hardware memory. It also provides the protection of system resources. It needs to do all this correctly. And then finally, previous research has shown that there are bugs in these virtualization layers. So bugs have been found in four of the major hypervisors and CPU emulators. So it's large, it's complex, it's buggy. Manual analysis and testing is already being done, and it's just not enough. We're really relying on this layer to be correct. We need to have some way to verify that it actually is correct. So this is what the work that I'm talking about today is, what my thesis has been on. How can we have confidence that this layer of virtualization is correct and providing the security properties that it claims to be? So, and in my work, I've looked at existing hypervisors. So not building a new hypervisor from the ground up, but looking at existing code that's in use. What can we do to increase our confidence in its security? Here's a brief outline for this part of the work. And I'm going to start by talking about some security properties. What are the properties that, if we could prove they are secure, would really give us gains in the security of the system, give us really added confidence in the security of the system. Then I'll talk about one of the first big challenges we encountered, which was verification in the face of very large data structures. I'll talk about the techniques we developed to handle this. And then finally, the second piece of my thesis really grew out of the first. In the first half, I verified this virtualization software by building a model of the software and performing the verification on the model. Of course, what we really want to know is that the property is true of the original source code, not just of the model. So in the second half of my thesis, I've looked at ways to validate that the model correctly represents the source code. So we can say we've proven the property true of the model, and we know that means it is true of the source code. So let me start with the security properties. These are the key things that, if we verified them, would really make a big difference to the security of the system. I've already touched on two big ones here. The first is correct virtualization of the hardware. So the hardware provides security-relevant properties to an operating system. Rings of privilege is one, virtual memory is another. It would not be OK if, in the course of virtualizing the hardware, the virtualization layer got that wrong, right? And sort of those properties no longer held. The guest operating systems are relying on those properties to be true. We need to make sure they really are true, even in this virtual environment. And then the second one is this isolation between guests. We need to know that guest A cannot access the memory belonging to guest B. So that's a little bit about the properties that we might care about. That's what we want to verify. Let me talk a little bit now about what some of the challenges are in software verification. So there tends to be this trade-off between verification techniques that are fully automated and verification techniques that give a more complete verification result. So in the fully automated space, we have things that fall along the lines of testing, so differential testing or fuzz testing. And there's been a lot of previous research looking at how to make testing techniques so that we can gain really high coverage of hypervisors and CPU emulators. So testing is great. It's great for finding bugs, and there's been some great research in this area. But the result is not full verification, right? We don't have a proof that there are no bugs. We just know that we have found a whole bunch of bugs. So on the other side of the spectrum, we have techniques that can give full verification results. So for example, theorem proving. And here, the work in this area has been to start from the ground up, design a hypervisor or emulator that is designed for verification so that sort of with theorem proving and other techniques, the end result is a fully functionally correct hypervisor. And then somewhere in the middle, we also have what I'm calling just small modular designs. So these are hypervisors that maybe a design has been proposed or even built. Verification hasn't been done, but the design is meant to be small and verifiable. It's meant to be amenable to verification at some point in the future. I am looking at existing code, so I want to be able to tackle existing hypervisor and virtualization code that's being used today. So I want to be, and I also want to be somewhere along this line where I make a nice trade-off between the automated and fully verified. So model checking falls along this line and tends to satisfy my criteria. So that's what I'm using. Here's a very high-level view of how model checking works. You start out with some source code as your input, and there's usually some translation to a model that happens. This can be done manually, or maybe there's some way to automatically extract the model. And then you have some property that is in the work that I'm looking at. It's always a safety property. So it's some invariant about the system. So for example, maybe you have the property that x is greater than y, and you want to know that at all points of execution, at all states of the system, it is the case that x is greater than y. So this is a property you input into the model checking engine, and the engine will take the model, take the property, and it can put out one of three results. So the first is proven correct. Yes, it is true. This property holds, and at all states, all possible states, x is greater than y. Another is no, it's not true. And in this case, the model checking engine will usually output a counterexample showing when x is not greater than y. And then the last one is I don't know. So the model checking engine can't prove that it's always true, but also couldn't find a counterexample. And in all these cases, the model checking engine is exploring the state space of the system, either concretely or symbolically, and at each state of the system, checking that this property holds. So coming back to the properties we want to verify, I talked about two really big ones. I'm going to start with memory isolation. Sort of in my work, I started looking at memory isolation, and then this grew into a large project. So this is what my thesis has been about. And this is looking at making sure that guest A cannot access guest B's memory. Kind of a couple things I want to point out here. One is that reasoning about this means reasoning about the management of virtual memory, so the mapping of the guest's view of memory down to the physical memory. And the software that manages that is complex. And then the second is a couple of caveats. One, I'm talking about memory isolation. This is not the same as isolation. So for example, side channel attacks might still be possible. They are real attacks. They're important to consider, but they're outside of the scope of my work. And then the second one is I'm really looking at this from a logical or algorithmic point of view. I want to know that algorithmically, the software that manages the virtual memory is doing it correctly and in a way that is secure. So for example, things like memory safety are outside of the scope of my work. I'm not considering memory safety issues. So for example, array out of bounds accesses. Again, an important problem, but orthogonal to what I'm doing. So that would also need to be verified, but it's a separate problem. So here's a concrete example of something we'd like to verify and that we want to verify. This is taken from the Box CPU emulator. So here you have the address translation from a virtual address down to a physical address. This is your sort of typical page walk, a picture of your page walk. You have the virtual address. It's used to index into a page directory, and then that is used to index into a page table. And then you have a physical address that points to the final page in memory where the data resides. In the Box CPU emulator, this data structure exists and is managed in software, but this page walk has to be done for every virtual address that gets translated. So as an optimization, the Box CPU emulator introduced caching of previously translated addresses. So this is called a translation look-aside buffer, just as it is in hardware, but this is in software and managed by the Box CPU emulator. So in security, anytime an optimization is added and it's on a security critical path, a good question to ask is the optimization correct? Is it messing with anything? You thought it was correct, and now you've added an optimization, you've added complexity. Is your system still correct? So, and that's the property that we looked at here. So particularly, is it the case that at all points of execution, at any state of the system, is it true that an address translated using just the page tables returns the same result as an address translated using the TLB optimization? So this is the first problem that we looked at, and we quickly realized that model checking just won't scale for this problem. The page tables and the TLB data structures are now all part of the state space. So all of that state in memory is part of the state space that needs to be considered during model checking. And so now we just have the state space explosion problem. How can we get model checking to handle such a large state space? So the solution is this sort of methodology, which we call S2W, for handling the verification of very large data structures. And this is the first piece of my thesis and the thing I'm going to talk about now. So S2W stands for small and short worlds. We sort of have two pieces to it. First is the small world. This is a well-known technique from testing. You know, if you want to test a very large data structure, one technique you might do is to take just a scaled-down data structure with only 1 or 2 entries and do all your testing on that. So we take the idea of using a scaled-down model, and we apply it using abstraction. And the abstraction is what makes a state space manageable for our model checking. So for example, in a system with 2 very large data structures, we might model 1 entry in each data structure concretely and let all other entries be fully abstract. So at each state of execution, all the other entries are allowed to take fresh symbolic values, variables. This makes our state space much more manageable. So the second piece of this is a short world. And this is basically bounded model checking. And again, bounded model checking is a well-known technique in the testing world. It's great for bug finding. So in general, sort of here's how it works. You have some property phi that you want to prove as an invariant of the system, or you'd like to test that it is an invariant of the system. Maybe here's what your system looks like. The first k states of your system looks like this. And you can just execute for k steps and show that the invariant phi holds at the first k steps of execution. So this is bounded model checking, and it works well. And if you find any bugs within the first k steps or violations of this invariant, you found a violation. The problem is you don't know what happens at the k plus 1 step, k plus first step, right? And so we don't have a proof that the invariant always holds. We only know that it holds at the first k steps. We want to be able to prove that the invariant holds for all states of the system. So what we do is we use the reachability diameter of the system as our bound in bounded model checking. So the reachability diameter is the length from any starting state of the system to any possible reachable state. How many steps of execution does it take to get to any reachable state from a starting state? So we found, so in the second piece of the work, we developed 2 techniques for finding what this reachability diameter is. In general, it's a hard problem, but we have 2 heuristics that work really well for the types of systems we're looking at. The reachability diameter tends to be small for the types of systems we're looking at, making this bounded model checking feasible. I'm not going to talk more about the abstraction that we use in the small world, just because it's very straightforward and not that interesting. I'm happy to answer questions about it. There's just not much there. So I am going to talk more about how we figure out what the reachability diameter is. So here's how we find out what the reachability diameter is. We take advantage of this fact, which is if every state reachable in k steps is also reachable in k minus 1 steps, then we can say every reachable state is reachable in k minus 1 steps. So to make it a little more concrete, we can say if every state reachable in 3 steps is also reachable in 2 steps, then we know every single reachable state is reachable in 2 steps. So to see why this is true, let's just walk through a short example. Here's our state space with a single initial starting state. And imagine, here's one of the states that's reachable in 3 steps of execution. And we have some way of showing, let's say, that it's also reachable in 2 steps. We have some way of knowing this is true. And let's say for any state reachable in 3 steps, we have some way of proving that it is reachable in 2 steps. So we know it's true for any state reachable in 3 steps. Then it's true that any reachable state is reachable in 2 steps. Here's a state that's reachable in 4 steps. Well, we already know that the third state in this trace is reachable in 2 steps, right? That's from our previous, what we've previously proven. And now this reduces to the original problem. Here's a state reachable in 3 steps. And again, we've proven this is reachable in 2 steps. So we know that this state will be reachable in 2 steps. So, and you can repeat this for every state. So coming back here, if we have this, if we can prove this first part of it, then we know what our bound is to use for bounded model checking, right? We know what our reachability diameter is. We can use that as our bound in bounded model checking, and we know we've explored all the states of the system. So the tricky part is how do we prove this first piece of it? How do we know if every state if every state is reachable in 3 steps, it's also reachable in 2 steps? Another way to state this is for all input traces of length 3, there exists a 2-input trace with the same end state. In general, this is a hard thing to prove. Proving these quantified Boolean formulas with the alternating for all exists is difficult. And if you think back to the model checking, you can see why. So proving this using model checking means exploring all input traces of length 3, and for each of those traces, exploring potentially all traces of length 2. And you can see how this quickly explodes once you get past the numbers 2 and 3, right? 3 and 4, 4 and 5 can grow very large. So instead, what we did is we came up with 2 heuristics, and the heuristics basically give us a way to instantiate the existential qualifier, so that there exists part. So basically, we take some educated guesses about what might be the 2 input traces that are going to get us where we need to be, and then we prove that those guesses are sufficient, and one of those guesses will always work to get us to the same end state. So the key is to come up with some smart guesses about what those 2-step sequences might be. And we have 2 heuristics. The first one is the subsequence heuristic. So one way to instantiate there exists is by just taking a subsequence of the 3-input trace. So again, I'm just using 2 and 3 as an example here. If we have a 3-input trace, we can try all possible 2-input subsequences and see if one of those gets us to the same end state. So for example, here's a trace with inputs A, B, and C. If we try the subsequence just AC, this does not take us to the same end state, so maybe we would try the next subsequence BC, and we can see this does take us to the same end state. And if we can try this for all possible traces of length 3, and show that for all of those, one of the 2-input subsequences will get us to the same end state, then we know all states are reachable in 2 steps. So this works well. If it doesn't work, here we have 2 and 3 input traces. If this doesn't work, you can try increasing the length of your trace to 3 and 4, and you can keep going until eventually you find a bound. But maybe the problem becomes too large before you find the reachability diameter. And so in that case, we go to our second heuristic. So the first heuristic was great, the subsequence heuristic. And when it works, it's fabulous, but it doesn't always work. And so then we need to go to our second heuristic, which is a little less simple to apply, but tends to be more effective. So the gadget heuristic sort of works by building gadgets. So if you think about a simple system where maybe you have a single starting state, and you can, in your head, kind of enumerate what all the possible end states are, and there are only 3 end states. And you can also, in your head, think about what it would take to get to any of those states. So you can think, well, inputs A and B will cover those 2 states, and input C will cover this state. Then you sort of, each of those traces is what we call a gadget, and you have just covered the state of the system. You can just take the longest gadget, in this case, a 2-input trace, and that's all you need to use as your reachability diameter. 2 steps will take you to all states. So of course, we're just sort of guessing here about what our set of states is. So to prove it is that our gadget set is complete, we use the same technique as before. We show that for everything reachable in 3 steps, at least one of the gadgets will get us there. So for example, we just try all three input traces. So we try AAA, and we see it gets us to a state we've already seen with one of our gadgets. We try AAB. We see that also takes us to a state reached by one of our gadgets. And we can just keep doing this for all 3 input traces. And if for all of them, one of our gadgets will take us there, then we know we're good. Of course, you might be wondering, if our system is so simple that we can just sort of enumerate the state space and what it takes to get there, we don't need this technique at all, right? The problem is that the system actually looks a little bit more like this, where the input is parameterized in some way. And depending on the input, you might go to one of very many different states, sort of in a group. So the state space is in some way partitioned. So for example, we have the input A with a parameter V0, followed by B with a parameter V1. And if you go back to our TLB example, you can think these inputs might be instructions. So maybe the input is translate an address. and the parameter is a particular address to translate. And depending on what the parameter is, a particular entry in the TLB might get updated. So now we have very many more states. It's too complex to just think about the whole state space of the system, but we still have just a couple of gadgets in this case, and the gadget is still just, the longest gadget is still just 2 inputs. And again, we have to prove that this is a complete set of gadgets using the similar technique as before. In particular, the kinds of questions we're looking at is, are these heuristics practical in the real world for the types of systems we're interested in? Are the abstractions well done? So are the abstractions too abstract, and we have lots of spurious counterexamples during model checking? Are they not abstract enough, in which case our short world becomes very long, so that reachability diameter becomes too long to be manageable? So these are the questions we're looking at during evaluation. We looked at 6 case studies. I'll talk about 3 of them here. One is the box's address translation, the example that I showed, where we were looking at a translation done using the TLB optimization, provides the same results as a translation done without the optimization. The second is we built a model of content-addressable memory-based cache, and we showed that if data is present in the cache, then it will be equal to the data in memory. And then the third one was we built a model of shadow page tables, and we proved a property about guest-host isolation. So in all of these cases, our bounded model checking did not return any spurious counterexamples, so that's a good indication that we're choosing our abstraction well. And then the results are that verification could complete, and so this is a sign that our short world is feasible. So you can see the longest one was the box's address translation function. That had a short world of 8 steps. The others were much shorter. And for the box TLB, the verification took 2 hours, and the others were, again, much shorter. And if you compare this to just sort of vanilla model checking just wouldn't complete, right? You need to keep going forward until you've explored the entire state space of the system, and the state space is just, for all intents and purposes, infinite. It's not, but it's just so large. So in conclusion, we have the S2W technique. Verification using this is sound. We know that if verification succeeds on our abstracted model, we know that the property is true of the original model. So, and it's true no matter what. So this is important in security, right? There's no way that the adversary, no matter how hard he or she tries, could possibly find a bug. We've proven this property holds. And then in doing this, we took some well-known techniques from the testing world, but we combined them and applied them in such a way as to give us sound verification, so a stronger result than just testing would provide. And the result is that we have verified these security properties related to memory isolation, and we've made verification of those properties practical. So the first piece of this thesis was really concerned with what's happening in this model checking engine. The result here, though, is that we've proven properties about the model. What we really want to know is that the properties hold true of the original source code. And so in the next piece of this talk, I'm going to talk about techniques that we can do, or a technique we can do to give ourselves increased confidence that the model correctly represents the source code, so that if a property is true of the model, we can know it's true of the source code. So I'll be looking at this piece of the problem. So I'm calling this model validation. Kind of here's the question that I'm posing. Given the source code and the model that it's extracted from the source code in some way, is the source code equivalent, or are the behaviors of the source code a subset of the behaviors in the model? The approach is a 3-step approach. In the first, we use symbolic execution to find paths through the code. So we explore the code using symbolic execution. For each path, we take note of the path constraints that led to that path, and also the resulting output. And this may be a symbolic result. And then finally, for each of these pairs, so each path constraint and output pair, we check this against the model, and we show, or we check that this pair exists and is valid in the model. So here's an example that I'll walk through. Again, this is from the box translation function, address translation function. So this code is just saying, if the current privilege level is equal to 3, then there's a page fault, so some protection check has failed. Otherwise, page fault is equal to 0. And here's what the corresponding model looks like. And this is saying if the 0th and 1st bit of the current privilege level are both set, then we'll set the page fault. Otherwise, page fault is 0. So here's our code and our model. In the first step, we use symbolic execution to explore the code. So the first path through the code will take the then branch of this if statement, and it'll output this pair. The constraint is that the current privilege level is equal to 3, and the result is that the page fault is equal to 1. In the second path explored, it'll take the else branch. And here, the constraint is that the current privilege level is not equal to 3, and the result is that the page fault is equal to 0. So we take these two pairs, and then we validate them against the model. So here's our model again. We take the first pair, and we check, is it true? Is it valid that whenever the current privilege level is equal to 3, it's always the case that the page fault, the resulting output will be a page fault equal to 1. So we can query our model with this, and the result is, yes, it is true. The next pair is that when the current privilege level is not equal to 3, is it always the case that page fault is equal to 0? Is this a valid statement? And again, we can query our model. And here, the result is, no, it's not true. And we get a counterexample back. And the counterexample shows, oh, well, when the current privilege level is equal to 7, the 0th and first bit will both be set, but it's not equal to 3, and a page fault is resulting. So here's an example of, and this was actual code taken from the Box CPU emulator and an actual bug in our model. And it's sort of an example of the modeler going through had this implicit assumption about an invariant of the system, right? And it was sort of a natural assumption, too, that the current privilege level is never going to go above 3, sort of probably didn't even think about it when writing the model. But it's actually, a result is that the model has behaviors different from the source code. So our evaluation, we looked at 2 case studies. And actually, the evaluation is still ongoing. But we have 2 case studies so far. And the questions here are, is this technique effective? Does it find bugs? And is it even necessary? Is this something we should be worried about? Do we need to worry about finding bugs in our models? So the first one is this box address translation function. This is the example that I showed earlier and that we used in our S2W work. So it's a small function, less than 100 lines of code. But there is some interesting behavior here. So 219 paths were explored. We used the CLI symbolic execution engine. And it's a very well-studied model. So we built this for our S2W work. We had used it extensively. Multiple researchers spent many hours looking at it, using it, debugging it. I felt very confident that this model would be correct. And in fact, I was just using this not as a case study so much, but just a way to kind of get the technique up and running, see that, get all the kinks worked out, and then I would go and apply it to other systems. But actually, during model validation, we found 5 bugs in our model. So this just points to how necessary this model validation step is. Even this small, really well-studied model still had 5 bugs in it. The second case study is looked at the traffic collision avoidance system, the TCAS. And this is a system used by planes to help avoid crashes, used by pilots to help avoid crashes. So it sits in planes, and it allows 2 planes to communicate with each other, and it's safety-critical software. The implementation I looked at is a simplified version. The actual software is very complex. So I looked at a simplified version taken from the software engineering literature. So this is a version that is used in the literature for testing techniques, for evaluating different testing techniques. It is, the version that I was using is 173 lines of code, so slightly bigger than the box example. Has 9 procedures, so there's some interesting behavior in there. And then also what is great about this is that because it's from the testing community, they had 23 different versions of this system, each with a different fault injected into it, and each fault is meant to be the kind of bug a developer might mistakenly, might have in their code. So what we did is we could create 23 different models, each with one of these injected bugs into it, and use our model validation technique to see whether we can find this bug. So we did that. And it was successful. Our model validation found all the injected bugs. So that's a good sign. Not only did it find all the injected bugs, but just anecdotally, it found 2 other bugs that were across all versions that were unintentional. So if we had a version, we had done the model validation, it was great. And then the researcher who was building the 23 additional versions made some optimizations, and along the way introduced 2 more bugs without even realizing it, right? And so again, this just points to how important this step is, this model validation step. It's so easy for these bugs to make their way into the model because typically the modeler has some implicit assumptions about the environment or about invariance of the system that aren't really thought through, and so it's easy for these bugs to exist in the model. So kind of just to sum up this piece of the work, this model validation step is important. Even really well-studied models are likely to have bugs. A simple approach is effective. So using symbolic execution to explore the code and then validating the path constraints and results against the model works. Given complete path coverage, so if we get complete path coverage from our symbolic execution engine, then we have full validation that the model is a safe abstraction. And we know a property proven true of the model will be true of the original software. And then finally, model validation really just strengthens the results of other verification methods like model checking. Okay, so that wraps up my talk about my thesis work. I'm going to move on to talking about some work that I've done in looking at secure hardware using formal methods as applied to hardware. So one project I did, this was sort of a design for verification project, and it was verifying an electronic voting machine. So this is a DRE, direct recording electronic voting machine. This is the kind of voting machine where a user interacts directly with typically a touch screen. So there's no paper ballot. And the question we wanted to ask here is, as the user interacts with this machine, they have no way to check what's actually happening, inside the state of the machine. We wanted to know, is the machine correctly capturing the user's intent, the voter's intent? So I built a machine. It was, again, this design for verification, built it in Verilog, synthesized it down to an FPGA. It had a touch screen daughter board attached so we could have a little prototype voting machine. And it used the ran verification directly on the Verilog code. The challenge here, though, is in order to verify something, you need to have a formal specification of what is correct. But in this case, what is correct is sort of in the voter's mind, right? They have a mental model of what's going on. We need to know that that's actually what's going on, but it's difficult to formalize, how a user is thinking. And when a user sees a screen, what kind of implicit interpretations are going on about, how they think the state of the machine is. So that was the challenge. The solution was to combine systematic testing with formal verification. So in general, user testing is not sufficient for verification. It's good for bug finding. In the case of a voting machine, the input traces are infinitely long, right? You can move forward and back between contests as often as you want. And so in general, testing is not enough or is not helpful in proving properties. But in our case, it was sufficient. With our design, which was a modular design, and with our properties that we verified about the determinism of the system, about isolation between contests, we were able to come up with a set of finite test cases that if they all pass, the test cases along with our proven properties combine so that we can prove correctness of the system. And we have a proof that the system will behave correctly and in accordance with how a user expects it to behave. So next piece of work I'm going to talk about is research I did while interning at Intel. This was in Intel's security group. So this is the group responsible for sort of looking at all the Intel upcoming products and looking at them and making sure that they are secure. So I was looking in particular at the Haswell microarchitecture. This is the microarchitecture that is coming out this June. And I was looking at the page miss handler. This is the module that satisfies a page miss request. So if there's a TLB miss, this module does the page walk. So I was doing verification for security. But there is already a verification team in Intel, right? Intel uses verification techniques extensively. They verify their hardware designs before shipping them out to the fab team. But they didn't have this verification for security. And that was really what I was doing. It was a pilot project with the security team to see, are there ways in which verification for security differs from just verification? Is there an added benefit to incorporating verification into the security group's workflow? So kind of what I did there was, looking at this one particular module, identify the security properties of interest, figure out what are those properties that we care about from a security point of view that maybe are the kind of functional correctness team isn't considering. Then ran explicit state model checking using Intel's internal tools. And the result was I found a really complex security critical bug. So the pilot project was a big success. And as a result of this, the Intel security team now has 2 engineers who do this verification work full time. And it's interesting, or it was interesting to me, at the start of this, I was kind of talking to the verification group at Intel, who sort of had, you know, the attitude of, well, we do verification already. I don't see what this verification for security is. But it turns out it really is different, right? You're sort of looking at verification is you're only verifying the properties that you ask, the questions that you ask, right? And so when you have a security-focused question and property, you can get different results and find new bugs. Okay, so then the third piece that I'll talk about is a project I did on detecting malicious hardware. This was looking, it was actually sort of an attack project. There had been previous research that proposed an algorithm for finding circuits, malicious circuits inserted at design time. The basic idea was circuits that seem to be unnecessary during all of the testing perhaps are malicious, and they should be flagged as suspicious. So I was able to show that actually the algorithm could be broken. It's possible to inject malicious circuitry into the design that gets used during testing, but that does not trigger the malicious behavior, so it's not detected. And kind of just sort of the result of this kind of just highlighted the need for a systematic analysis for these detection techniques. All right, so I'm going to switch gears one more time and talk about some ideas for possible future research directions that I'm excited about. So one, I've talked today about looking at some security properties in hypervisors. I think there are a lot more really interesting properties here. There's a lot more to explore. So one is, I/O isolation. The device management and device assignment is also virtualized. So, peripheral devices, it's also virtualized by the hypervisor. And it's important to know that the virtualization of these devices doesn't violate isolation. So you don't want one guest to be able to read or inject into another guest's input or output stream. And then other properties about correctness. So hypervisors are used for as sort of a tool for security. So we would like to know that some of these things are correct. So maybe sealed storage and remote attestation are done correctly. And then finally, I think the larger question here is, how strong of a statement can we compose? Can we take these individual security properties and compose them into a higher level statement of overall security? How strong of a statement can we make about the security of the hypervisor or emulator? Another thing that I am interested in looking at is going down a lower level, looking at the security of processors. So, they provide these really security critical primitives that we all rely on without even really thinking about them too much. So privilege levels, rings of privilege, execute permissions of pages in memory. And the industry folks do put a lot of effort into making sure the hardware meets the specification. But the specification itself is not really tested, right? The specification is large and complex. And even worse, it doesn't fully exist. When I was interning at Intel, I learned that a lot of the specification exists in someone's head, a designer's mind, and I would need to go and talk to a designer to find out kind of what the spec was. The specifications that do exist are full of non-determinism, and they're just holes. We don't know what's happening. The behavior is undefined, or any behavior maybe is possible. So the question I want to ask is, is it possible that the specification itself, so not the hardware, but the specification for how the hardware interacts with the software, is it secure? Are there any pieces there that we haven't thought about fully, that maybe there are areas where a correct hardware implementation that meets the specification can have security vulnerabilities in it? And then the last piece is to look at systems that involve a human in the loop. So we know in security, a provably secure system is not secure if it's not used as intended. So we need to know that it's actually, once we put it out there, it's actually being used as intended. So there are some safety critical systems, medical technology, aviation software, some web browsers are another security critical system where we would like to verify security properties of this user-facing code even in the face of having a human in the loop. Are there ways to do this? So just to sum up, my first part of this talk was talking about my thesis work, where the result was a new technique for applying formal methods to verifying security properties of large data structures, and this is directly applicable in virtualization software. And then the second piece of that is model validation can strengthen the results of that model checking. And as a result, we sort of have made inroads toward verifying this legacy virtualization software that is used in these security critical systems. So thank you, and I'd also like to thank the researchers that I have collaborated with on the projects I talked about today.
OK, we have time for some questions.
In your 3 model checking case studies, I was really surprised that the number of transitions explored was so short. It was like 2, 4, and 8. I mean, is there a plausible explanation for that?
Yeah, it's because of the abstraction that we introduced. So because of the abstraction, we only needed to look at, so for example, a single entry in the TLB. And then a single entry in the TLB, each step of that execution was parameterized. So one step might be to translate some address, where we could explore all those addresses in parallel. So it's one step of execution to translate that address. Another step may be to invalidate that entry in the TLB, those types of things. So it was really the abstraction that allowed us to shrink the reachability diameter.
I mean, maybe it was short, but maybe it was wide. Do you have other metrics for how big the exploration was, like number of states or transitions?
Before we introduced the abstraction or after?
Well, no, that you actually explored.
Oh, so okay, so another way to think about it is, each entry in the TLB is 60 some odd bits, so that's like 2 to the 60th possible states, right? The way the state space, so the way I think about it in my head is it sort of looks like a wheel, so it has that radial diagram where there's an initial state, and from the initial state, it doesn't take very many steps to get to any reachable state, but there are very many spokes to that wheel.
Yes, you said the side channel attacks are out of scope, but can you talk about how we could use these techniques to explore them, or can we do that?
Side channel attacks, I think, one way that has been shown to be effective but tends to give reduced functionality is to provide, to isolate resources in a more constrained way. So for example, timing isolation, where each guest gets the same time slice, that type of thing, where so that you make the usage predictable. The result is that you have slow down your use, and it's maybe not usable. I haven't explored ways to verify that you have these, you've like sort of proven properties that would prohibit side channel attacks. But I could imagine potentially there's a way to, if you're going that route of you want to make sure every execution takes the same time slice, you could use verification for that. There are other problems, like power side channels. It's hard to imagine how formal verification of this type would work for verifying like sort of the power usage. And it's a little bit too far outside my area of expertise to know if there are other types of formal verification that could tackle that. Yeah.
Can these methods be applied for cache coherence protocol verification?
Yeah, so there has been a lot of work in cache coherence protocol verification. I haven't looked at specifically whether S2W could be applied. My guess, sort of my intuition, is that it really could. That we could map, instead of a data structure, we could map like the nodes of the system to entries in the data structure. One of the reasons it works so well on the types of data structures we looked at is that every entry in the data structure is symmetric. The data structure is symmetric, right? Every entry kind of updates in the same way as all other entries. And that is true of nodes in a cache coherency protocol. So my guess is that it could be applied. I haven't done any work in that area, so there very likely are new challenges there, and maybe there would need to be like new tweaks, but at a high level, I feel like it would apply.
Okay, since there aren't hands, I'm going to ask another question. I'm curious to hear, so in thinking about your talk and kind of grounding in the context of computer security, if someone were to come up and ask you, what are the biggest risks in computer security? I'm curious what you'd say.
Biggest risks. So I feel like there are a couple of big risks here. So one is the components of a system that are ubiquitous, that we rely on for everything. If one of those could be exploited, if some vulnerability is found that could be exploited, I think that would be a big risk. So for example, CPUs, we rely on them, they're in everything. If there was some vulnerability there that could be exploited, you would have widespread attack. So in that sense, I think that is one of our biggest risks.
Okay, well, let's thanks, Cynthia. And we have a little bit of time if people want to ask some questions.